Hello student, welcome to the wave optics course. So today we have lecture number 35 and in this lecture we are going to discuss about the double slit diffraction problem. So we have lecture number 35 today and going to discuss about the double slit experiment, but before that let me remind what we had so far, that if we have an aperture in the form of single slit and allow the light to fall, these are the wave front that is coming and these are the plane wave front because we are dealing with front upper diffraction pattern. Then at some point here, if I place a screen, then we are going to get a diffraction pattern like this. We have a maximum intensity here, then in the geometric shadow region we have a distribution of the intensity in a specific form. So, this is the intensity distribution I, which essentially a function of theta, and that is I naught sine square beta divided by beta square. This is the form we derived, where beta is a quantity which is pi of d divided by lambda and sine theta, where theta is a angular distance. For example, if I want to find out the intensity at angle theta, so this angle is the theta angle and this is the point where this intensity is there. So, if I put the value of the theta, then I am going to get the value of the beta, and based on that I can calculate what is the intensity of that particular theta point, where d is the separation, this is the d is the separation of the width, and the fringe, if practically the fringe will look like this kind of lines. So, I have a central fringe like this and then we have another fringe here, we have another fringe here and so on. This is roughly the fringe pattern, difficult to draw in principle, but I am trying my best. So, if you do the experiment, then you are going to see like these patterns, and if I draw the distribution, intensity distribution, it should be bright, then dark, then bright, dark, then bright with reducing intensity like this and so on. Okay. So, this peak corresponds to this bright, this peak corresponds to this bright, and this dark region is this regions, and that distribution is over theta. So, we calculate from the first principle everything and then derive this expression. So, today we are going to extend this calculation not only for single slit, but a double slit. So, double slit is a very important experiment in the physics, and what happened, let me describe. So, this is a double slit setup, and this is a double slit setup, and plane wave fronts are coming, and then it reaches to this point, and from here we have wave fronts that is emitting, and these two wave fronts that is emitting here will going to interfere over the long distance. And if I want to find out some point at P, the intensity, we will going to see some intensity pattern. So, diffraction and the interference both will take place together here, and we will going to see a pattern here in the over the screen. So, that calculation we will do today from the first principle. The way we calculate for single slit, we will continue with this and then try to understand what is going on. So, let us now draw again the setup. This is the experimental setup and a schematic diagram to show how this experiment is happening. We have a light source, and then we place this aperture double slit, and then at some point we will going to see some distribution, and here we like to draw the overall structure. So, this is basically the double slit. This is the opaque region. This is slit number 1 and this is slit number 2, and we need to define the coordinates properly to do the calculation. So, I am defining this dotted line should be my x, and along this direction perpendicular to dotted line is y, and these slits are exactly on the y axis. So, this point is so let us first describe what is the separation between two width two slits. A is a separation between two slits. So, this is A, center to center, and individual slit width from here to here, it is B. So, that is our definition, that A will be the separation between two slits, and that we define by this, that the central point to central point of this slit is A, and B is the individual separation in the width of the individual slit. So, now we need to just understand what are the coordinates, and then we are done. So, if this is, so let me write down the coordinates of this point, this point, this point, and this point. So, if this is y equal to 0, then the coordinate of this point, so from here to here it is, from this to this is a by 2, and from here to here, from this region is this is b by 2. So, this is a by 2 minus b by 2. So, this coordinate of this point is a minus b divided by 2. Similarly, the coordinate here is minus of this point is minus of a minus b divided by 2. This is important that once we fix the coordinate, then I can integrate over, and then I am going to find out what is the intensity at some point. But before that, the geometry we need to understand. We need to understand how these coordinates are there based on the definition we have A and B. This point here, it will be from here to this point is A by 2, and I add this, which is B by 2. So, it is simply A plus B divided by 2. This is symmetric. So, this point will be minus of coordinate of this point will be minus of A plus B divided by 2. So, all the points I define. Once we define all the points, so I need to write A is the separation between slits, the separation between the slits and B is slit width. Individual slit width. So, obviously, EP, that is the field at point P, if I write it EP, it is some amplitude E naught, and then it is the integration of all this aperture to e to the power of I delta and dy. Note that here delta is a phase difference, and that is k y of sin theta. So, I just need to calculate this integral, because I know that what should be the phase, and all the points I need to calculate the phase over this integral, and this is the simple expression to find out the total intensity at that particular point P, where this is the geometry that it is shown here. This is the value. So, let us now integrate then. So, EP will be then simply E naught integral of minus lower point A plus B by 2 to other point A minus B by 2 e to the power of I k sin theta into y dy plus another contribution. This is for slit 2, and for slit 1 it is E naught, then lower limit A minus B by 2, upper limit A plus B by 2 e to the power of I, and then k sin theta y dy. So, the contribution of the slit 1 and contribution of the slit 2 are simply added by this integral, and whatever the result I get, that should be the total field at this point according to the Huygens-Fresnel's principle. So, let us do this integral, which seems to be not that difficult. So, E naught I take common, then e to the power I sin theta y dy, it should be simply e to the power of I k sin theta and y divided by I k sin theta need to be calculated at these 2 points. This is the first integral. Second integral similarly. Same thing, only the limits will going to change here. Yeah. So, it should be E naught divided by this I k sin theta, I can take it outside, and then I put all the values. So, here we have I minus k by 2 and then a minus b sin theta, that is the first term, minus e to the power of minus I k by 2 a plus b sin theta plus e to the power of I k, then a plus b k by 2 sin theta, and finally minus e to the power of I k by 2, then we have a minus b sin theta bracket close. Okay, now I simplify because there are many terms a plus b, a minus b sin theta k by 2, these terms are present several times. So, I put few names. So, let beta is half of k b sin theta and alpha is half of k a sin theta. So, we have written this expression in terms of beta and alpha, then it should be little bit compact. So, then EP will be simply E naught divided by I k sin theta, and then if I rearrange, if I look carefully this expression, so what I can do that e to the power I k by 2 a sin theta, if I take common from here, So, this term is present here also. So, I can take it common and I am going to get some expression. Similarly, e to the power I k a sin theta, if I take common, then I will get some expression like that. So, if I do, then I simply get this e to the power of I alpha minus I alpha, rather if I take common, then I am going to get something like this e to the power of I beta minus e to the power of minus I beta. Then if I take e to the power of I alpha common, then I will going to get the same term back, the power of I beta minus e to the power of minus I beta. With the fact that alpha and beta, and that, let me write down the alpha and beta once again. Alpha was k by 2 a sin theta and beta was k by 2 b sin theta. So, E p, then it is E naught divided by I k sin theta, and that quantity I can simply, I can take e to the power I beta, e to the power minus I beta again common. So, let me do that actually. So, it should be e to the power of I beta minus e to the power of minus I beta multiplied by e to the power of I alpha plus e to the power of minus I alpha. So, this gives E naught I k sin theta. This quantity e to the power I beta minus e to the power minus of I beta simply turns out to be 2 I sin of beta, and the other term will be simply 2 of cos of alpha, and I can have this 4 of I can be cancel out here, this I, and I have 4 of E naught divided by 2 of k by 2, and I put another b and sin theta here, and I put this b here, and then I get cos of alpha multiplied by sin of beta divided by beta. I just want to put this sin of beta divided by beta term, so that I can write in a compact way. So, this k by 2 b, these things are basically beta. Okay, I make a mistake here. So, I will put these things later, because still this is sin beta. If I put this beta here, then it will be like this. So, next line actually, it will be 2 of E naught b, then it will be cos alpha, and now I write sine of beta divided by beta, because k by 2 b sin theta is beta, which is already defined here. So, essentially what we have, the intensity distribution is something like this. Intensity distribution should be proportional to the mod of E p square. So, intensity at point P will be this. So, from here I can write that the intensity at this point P should be I naught, then cos square alpha multiplied by sin square beta divided by beta square. That is the thing I have. So, that is the intensity distribution or intensity pattern we have, where alpha and beta we defined several times. So, let me write down once again, because these are important quantity. This is k by 2 a sin theta, or this k by 2 sin theta sometimes written, because k is 2 pi by lambda. So, it is pi a by lambda sin theta, and beta, which is k by 2 b sin theta. It is again k is 2 pi by lambda. So, if I put this value 2 pi by lambda, then it should be pi b by lambda sin theta. Okay. So, that is alpha and beta. So, now it is time to draw that how this distribution should look like. So, I intensity is proportional to cos square alpha, and also it is proportional to sin square beta divided by beta square. So, I like to show the distribution here. So, the sin square beta divided by beta square distribution is known, because that we done for our single slit experiment, and cos square alpha is simply. So, let me first draw the cos square distribution. So, this will be the distribution of the cos square. This side also. Something like this. This is theta, this is 0 point, and this is theta, and that is the distribution, and this value is 1, because cos square alpha should have maximum value 1, it should not have a negative value. So, this value is 0, and I am plotting intensity here, intensity, which is a function of theta, but I am plotting individual functions. Now, how the sin square beta will look like? Sin square beta, on top of that, if I plot, let us plot in a different color. So, it should be like this. It should be like this. So, the blue line, this blue line is sine square beta divided by beta square plot, and the red line, this one, is cos a square alpha. This is the plot. So, red line and blue line, now they are situated as a multiplier. So, they are situated as a multiplier, means the original expression should be something like this. The original the exact or the actual distribution of the intensity will be this. We have an envelope here, and so on. This side also we have small these things rapidly diminishing to 0, and inside this envelope we have this distribution. So, this is the intensity pattern one can expect. Few interesting aspects will come, maybe we are going to discuss in the next class. Let me draw the intensity distribution here. Inside the envelope we have small peaks like this. So, there will be, in other words, there will be a modulation of the individual peaks, and this modulation will be taken care by sine square beta term, sine square beta by beta square term, and inside the term that we have is due to interference. So, here the interesting thing that we need to note is there are two contribution, one is cos a square and another is sine square. The cos a square contribution is coming due to interference of these two lights, that is coming from two slits, and the envelope that we are getting here is basically coming because of the contribution of the diffraction. So, this will be the final expression, final form of intensity over this, over this theta, and we will see in the next class that because of this overlapping of this two structure, there is a possibility that we are going to miss few of the spectrum, which we will call the missing order. We are going to calculate this missing order. Few question also may you expect in the exam or in the assignments due to this missing order problem. So, with that note, I would like to conclude here. We are going to discuss more about this spectrum of two slit experiment in the next class, and then we discuss in detail how the missing order can be calculated, etc. So, thank you very much and see you in the next class.